Hello, this is Stat135, Lecture 9. Last time we wrote a 95% CI for the parameters of the normal distribution in terms of the t and chi-square distribution. And today we're going to see other ways to write a confidence interval involving bootstrapping, parametric and non-parametric, as well as using large sample theory for the MLE. We're going to start with bootstrapping. First, parametrically. Step 1 is we take our sample, make a histogram, and guess a model that fits that histogram. Step 2, we check, we estimate our parameter using a MOM estimate, and then actually check that it's a good fit. And step 3, we use our model to with the estimated parameter to generate our sampling distribution, and then take the SD. To find the CI, we have our sampling distribution, and we find of theta hat minus theta, we find the 2.5 and 97.5 percentiles, quantiles, and then the 95% CI will be theta hat minus b, comma theta hat minus a. Now we don't know actually what theta is in this in the sampling distribution, so we approximate it with the with our MOM estimate. In other words, the estimate from our original sample, and we generate 1,000, let's say, MLE estimates using our model to get our distribution for theta hat minus theta. So this is actually we're going to call that theta star minus theta hat. And in R, we're going to find the quantile of that for 1 minus alpha over 2 and alpha over 2 quantiles. And the highlighted formula here then gives you a way in R to code this. So just make some quick comments about the code here. So my population is lambda 1, so I'm using rpos to get my sample of size 100. I overlay my sample histogram to the theory using a MOM estimate, which I found to be 0.89, and it looks like a fairly good fit. I then use rpos to sample from my model distribution with lambda equal my MOM estimate 1,000 times, and that gives me 1,000 numbers, of which I find the SD, which is my SE. So non-parametrically, we did this before. The difference here is that I'm resampling from my sample with a replacement. Which method is better? If you have a large sample, non-parametric is the way to go. If you have a small sample and you're fairly confident about your model, parametric model is better. To do a CI, I did this here for gamma, alpha, lambda, so a different example. And the highlighted formula here is the R code to find the quantile that we showed earlier. Moving on to large sample theory for MLE. The upshot is that for large N, the MLE estimate is approximately normal with mean theta 0. In other words, it's unbiased. And the variance is 1 over n times the Fisher information. The Fisher information is something that we now are going to introduce. So Fisher information for a single observation tells you how much information your single observation has towards determining theta. A single observation gives gives you a likelihood function of which the MLE is finding the max of that MLE of the likelihood, right? What theta maximizes the likelihood. So we're going to look at two examples. One is where your data is informative, coming from a normal distribution mu1, and one that's uninformative, coming from a normal mu25. So our parameter, unknown parameter here is mu. The log likelihood is a quadratic with facing down, and suppose that mu is 5. So I'm going to generate 1,000 samples, 1,000 individual observations, calculate the log likelihood for those 1,000 individuals, and look at 1,000 curves, my 1,000 log likelihoods. So the top is for the informative case, the bottom is the uninformative case. What do you notice about these? Well, from the informative case, it looks a lot easier to say what mu maximizes these log likelihoods. For the uninformative case, because the variance is higher, 25 versus 1, they're more spread out, these log likelihoods trajectories, and it's harder to pinpoint. So the slope, the tightness of the log likelihood is the key idea here. So we're going to define the score function to be the derivative with respect to theta of the log likelihood. And I'm going to concentrate now on the uninformative case. So I've sort of zoomed out here, so I'm looking at a wider range of mu values, going from -5 to 15 now. So, and I'm looking for at 3 different mu values. I'll indicate by blue, green, and red. You can see the range of slopes that you get. So the bottom picture here is a graph of the score functions versus mu, and you can see that you get pretty much the same range of the width of the range for blue, green, and red are the same, but the blue tends to be positive slopes. The green tends to be a mix of positive and negative, centering at 0, and the red tends to be negative slopes. And this information can be depicted by these histograms here. What I haven't shown you is what's happening for the informative case, but we're only going to really be interested in the case where mu is 5. So the case where mu is 5, what do you think? If you were to look at the informative case, would the spread of slopes be greater or less at mu is 5 for the informative case or the uninformative case? So for the informative case, I hope you can see that you're going to get a wider range of slopes for the case where mu is 5, right? So you're going to have some slopes that are pretty upward facing, some slopes that are almost flat, 0, and some slopes that are quite negative. So you're going to get quite a wide range because the trajectories are steeper. Okay, so you're going to get a wider range. So let me make these observations. So the above picture is only for the uninformative case. If the picture was for the informative case, the histograms would have been wider, more spread. At mu is 5. The histogram of the slopes of the likelihoods for the informative and uninformative case are centered at slope is 0. So in other words, the expectation of the log of the score function is 0, where expectation means average over all the outcomes of x. So large spread of the score at theta equals theta 0 means more informative. And that becomes the basis of our definition of Fisher information. So Fisher information is the variance of the score function of theta equal theta 0. And because the expectation is 0, we're looking for the case where theta is theta 0, the Fisher information can also be written as the expectation of the score function squared, and that follows from the fact that variance is expectation of variance of A is expectation of A squared when the expectation of A is 0. If the log likelihood is twice differentiable, according to lemma A, page 276 in Rice, we see that it's also equal to minus the expectation of the second derivative of the log likelihood. This has a nice interpretation as minus the average curvature of the log likelihood over all the values of x in x. So Fisher information has two equivalent interpretations. 1, variance of the score function. 2, minus the average curvature of the log likelihood over all x in x. Large Fisher information is good, so we'll be using the second interpretation. So for us, our working definition will be Fisher information is minus expectation second derivative of the log likelihood function. So that's it for today. I'll see you guys next time, and we'll look at some specific examples of calculating Fisher information and then calculating the